Hello everyone, this is Anthony and this video will be the start of a series me and Claudio will be making for AP Physics C, Electricity, and Magnetism. This video will follow Chapter 22 of Physics for Scientists and Engineers by Surway and Jewett, 10th edition. So the word electricity comes from the Greek word electron, which means amber, and amber is petrified tree resin. And the ancient Greeks knew that if you rub a piece of amber with a cloth, the amber will then attract small pieces of leaves or dust. So this effect can be replicated with a piece of hard rubber, glass, or plastic ruler. And we call this effect static electricity. Ben Franklin theorized that there are two types of charge, electric charge, positive and negative. And the reason he thought this was because if he took two plastic rulers and rubbed both of them with cloth so they both become electrically charged, and then attached one to a torsion pendulum, he would find that when he brought the other near the one on the pendulum would twist away from the other ruler, signifying that the two felt a electric repulsive force between each other. And the same thing happened with two glass rods. But if he took a glass rod and held it near a plastic ruler on a torsion pendulum, the pendulum would twist towards the rod, signifying that the ruler and the glass rod felt an attractive force between one another. And so it's said that unlike charges attract and like charges repel. And Ben Franklin also theorized that the amount of charge produced on one object was equal and opposite to the charge produced on another object. So the plastic ruler from above, after it's rubbed with a cloth and it becomes electrically charged, in the example above, the plastic ruler was negatively charged. According to Ben Franklin, the cloth received a positive charge equal to the magnitude of the negative charge. So no electric charge can be created or destroyed. It can only be transferred from one object to another. And most of the time, the transfer is through electrons, which we'll see in the next section. The structure of an atom. Only within the past century or so has it become clear that electricity originates inside the atom itself. This is because the atom is made of three different particles: protons, electrons, and neutrons. And so the protons have a positive charge, and the electrons have a negative charge. And the charge on the proton and electron are equal but opposite sign. And the neutron has no charge. So since the protons are always bound with the neutrons in the nucleus, they never are transferred from one atom to another. It's always the electrons that can leave an object or leave an atom and go to another object or atom, because the electrons are whizzing around in the volume surrounding the atom, and they're not really bound in the nucleus like the protons are. However, not every electron will necessarily leave the atom, because there's some really close to the nucleus that are really attracted to those positive protons, and those electrons are not going to leave the atom. Typically, the valence shell electrons are the electrons responsible for charging objects and transferring between objects, because those are more loosely bound. So that leads us to insulators and conductors. So as I have drawn here, in an insulator, all the electrons are going to be tightly bound to each nucleus, and they're not really going to be able to move around very easily or escape the material or atom. Meanwhile, conductors electrons are more loosely bound to the nucleus and can move around freely within the material. Notice they don't easily leave the material. They stay inside it, so the material itself, say a piece of metal, like this nail up here, is electrically neutral. Say there's a negative source of charge on the right side of this material. All the electrons will now be repelled from this source, and they can freely move to the left side of this brick here. Now say there's a positive charge on the right side of this brick. Some object is positively charged, and you bring it next to this brick. All the electrons are going to be attracted to this positive charge, and they can freely flow to the right side of this conductor. Now to sum up what we've learned, electric charge comes in two, quote, flavors, positive and negative. Opposite signs attract, same signs repel. So the law of conservation of charge. Since the mass in a system is always conserved, that means the number of protons, electrons, and neutrons are always conserved. And since electrons and protons are the particles that are charged in the system, charge is also conserved in a system where mass is conserved, which would be any closed system. And so the fundamental charge, E, is the least amount of charge that can exist besides zero. And it's equal to the charge on an electron or proton. They both have the same magnitude of charge but opposite signs. And so since you can't split an electron in half or a proton in half, this is the minimum amount of charge that can exist. And every greater amount of charge is an integer multiple of this fundamental charge. Now we are going to discuss Coulomb's law. And Coulomb's law describes the electric attractive or repulsive force between two charges. And so in the lab, Coulomb discovered that the electric force between two charges is directly proportional to the charge on each charge and inversely proportional to the square of the distance between the two charges. Similar to how the gravitational constant was calculated, Coulomb calculated his constant for his force law, which is about equal to 9 times 10 to the ninth. And it has similar units to the gravitational constant, Newton meters squared per Coulomb squared, in order for this force law to give newtons. And K is also equal to 1 over 4 pi epsilon sub naught, and epsilon sub naught is the permittivity of free space. It basically describes how easy it is to create an electric field in a vacuum, which will be discussed later. And now we also get a value for the charge on an electron or proton. This will be the magnitude of the charge without the positive or negative sign. And it's about 1.6 times 10 to the minus 19th coulombs. And so 1 coulomb of charge is actually very large. So most of the time we're going to be dealing with microcoulombs, nanocoulombs, or picocoulombs even, which is 10 to the minus 6th, 10 to the minus 9th, and 10 to the minus 12th, respectively. And so now we're going to do a side-by-side comparison of the strength of the electrostatic force and the gravitational force in the hydrogen atom. So the hydrogen atom has one proton and one electron, roughly 5.3 times 10 to the minus 11th meters in separation. And we can get the mass and charge of the electron and proton from this table here. And we already know the charge on the electron and proton is 1.6 times 10 to the minus 19th coulombs, the fundamental charge. And then the mass of an electron and proton is listed here, which will be substituted into Newton's law. And after substitution, we find that the electrostatic force is 10 to the 39 times stronger than the gravitational force. This is millions, billions of times stronger. And this can be summarized in this side-by-side comparison here by looking at the two constants. Coulomb's constant has a very, very large magnitude compared to Newton's constant. Newton's constant is on the magnitude of 10 to the minus 11th, while Coulomb's constant is on the magnitude of 10 to the positive 9th. Many, many times larger. Now on to the vector form of Coulomb's law. Now when solving force law problems, I do not recommend using vectors and plugging in the positive or minus signs into the charges. I'll go through an example right now. Say we have three charges. Say we have three charges set up in a line. We have a positive charge here, a positive charge here, and a negative charge here. Now say they are all an equal distance apart, distance A, all an equal distance apart. And say we want to find the force, the net force on the center charge from the other two charges. So we're going to start off with Coulomb's law, and let's go left to right. So we'll start with the other positive charge. So the force, you know what, we're gonna number these charges. 1, 2, 3. So the force on charge 2 from charge 1 is equal to K, say they all have an equal magnitude of charge, plus Q minus Q. So the force on charge 2 from charge 1 is equal to K, Q times Q over A squared, or K Q squared over A squared. Now that's the magnitude of the charge. Now the direction of the charge, since this is a repulsive force, it's going to be to the right. To the right. So that's how you should always solve a force law problem. Find the magnitude and then find the direction. Now if we want to find the net force, the force on charge 2 from charge 3 is equal to K Q squared, this is the magnitude of the force, over A squared. And what direction is this going to be? It's also going to be to the right. also to the right. So the net force, on charge 2, is equal to 2kq squared over a squared, directed to the right. Done. Now on to a proportional reasoning example. Two charged spheres are placed a distance apart from each other. The two charges are then released from rest and they begin to move away from one another. When the two spheres are 3 times the distance apart, one has lost exactly half its charge. What is the new Coulombic force each particle exerts on each other compared to the original force? So since they both move away, we know that they're both the same sign charged. So say they're both a positive charge. Say we have two charged spheres on some smooth surface, so friction is negligible, and they're just sitting on here. And now they're both going to feel a repulsive force away from each other. And the two forces are equal and opposite according to Newton's third law. And so let's find the original magnitude of these forces. So the magnitude of the electric force is going to be equal to k q squared over d squared, the distance squared. All right, so this is the original force, F original. And now we have a second situation where the two charges have slid a distance apart. Now they're actually 3 times the distance apart. Right, so this distance is now equal to 3d, 3 times d, and one charge has lost half its charge. So let's say this charge has lost half its charge. So this is 1/2 q, and this is still q. Now we can reason through this. Since the distance is now 3 times what it was, we know just from that the force is going to be just from that we know that the new force is going to be 1 over 3 squared the original force. Start. So we can reason through this. We know since the two spheres are now 3 times the distance they were, the new force is going to be 1 over 3 squared the original force just from the distance. And since one charge has lost half its original charge, the new force is going to be 1/2 the original force from that. So the actual new force, taken into consideration these two changes, is going to be the multiple of 1/9 times 1/2, or 1/18th the original force. We're going to look at a model for a particle in an electric field, which is going to be very similar to a particle in a gravitational field. So the electric field is defined as the ratio of the force a charge will feel divided by the charge on the charge itself. Very similar to the definition of G, the gravitational field. And the direction of the electric field is going to be in the same direction that a positive charge would hypothetically feel a force. And so this is called a test charge, meaning that it doesn't actually exist. We hypothetically put a positive charge in here without altering the electric field from the source charge, and we consider which direction that charge is going to feel an electric force from the source charge. This interaction can be thought of as, rather than the source charge and test charge interacting with each other directly through space, the source charge produces an electric field at every point in space, and the test charge interacts with the field rather than the source charge itself. That gives us another definition for the electric force, Q times E. That's the charge on an object in the electric field multiplied by the electric field at that point. And like how we did to find an expression for the gravitational field, we can equate Coulomb's law to this new equation for the force. And we notice that the charge of the object cancels out, and we're left with kq over r squared. When you're doing problems with this equation, it's important to consider the vector direction. So instead of just finding the magnitude with the force law like we did earlier, you actually have to draw the vectors and then add the vectors together. The net electric field is going to be equal to the sum of the contributions to the electric field from each source charge. Say we have 3 source charges, and we want to find the electric field at some point P. You would find the individual electric field from each charge and write the direction that field would propagate. So from charge, I'll do different color for each. 1, 2, and 3. From source charge 1, the electric field at point P would be directed this way. From source charge 2, the electric field would be directed this way. And from source charge 3, the electric field would be directed this way. And so you take the vector sum, that means you split each vector into horizontal and vertical components and add each component together. And from this, it can be implied that the electric field is also an integral, that is the integral of k dq over r squared. And even this integral is a vector. It's still important to pay attention to the vectors when evaluating this integral. And this integral will be evaluated later in the next chapter when we discuss Gauss's law with Claudio. And very often you're going to substitute dq as a function of r. So it can be equal to the volume density multiplied by dv, or the charge, or the linear charge density multiplied by dl, and then you can express r in terms of L, most likely, or it can be expressed in the surface charge density multiplied by dA. This table summarizes what we just learned about our model. Imagine a source charge that creates a field, and then imagine a test particle interacting with the field. Examples of this can include cathode rays, examples of this can include cathode rays, charged ions in a mass spectrometer, etc. Section 22.5, Electric Field Lines. So an electric field line is a useful way of depicting an electric field around a source charge. So we said before that the source charge has an electric field value at every point in space. So this can be written as a vector field, with the arrows getting shorter or weaker in magnitude as you move away from the charge. I'm going to cut out the time it takes me to draw this. So now that I have that drawn, instead of just drawing an infinite number of arrows like this, what we do is we draw a few long arrows. And well, you might say, well, what about the magnitude from the length of the arrows? We lost that information. Well, now the magnitude is viewed as the density of the field lines. So see down here, the field lines are closer together, and up here they're further apart, meaning the electric field is stronger down here and weaker up here. Some important notes about field lines. They always begin on a positive charge and terminate on a negative charge, as I'm illustrating now. Or if there's no negative charge present, the field lines extend towards infinity, which means just draw them pointing away from the positive charge with arrows towards infinity. And then likewise for the negative charge, they extend from infinity and end on the negative charge. And the number of lines drawn is proportional to the magnitude of the charge. What does that mean? Say, for example, you have a charge of minus Q. So you have a negatively charged sphere here. And say you draw 4 field lines. 4 field lines. Now say you have a second charge of magnitude twice that, minus 2Q. Well, now you would have to draw 8 field lines to remain consistent with your magnitude. and no two field lines can cross, which makes sense because the electric field only has one direction and one value at one point in space. This example will go over the electric field due to 3-point charges arranged in an equilateral triangle. So part 1 asks us to sketch the field lines. So since there's all positive charges here, we know that none of the lines are going to terminate and they all extend towards infinity. So we begin with the easy lines, which will be on the corners of the triangle. All right, now a trickier set of lines to draw would be the ones on the inside of the triangle. And so what do we have here? Well, let's start with the left charge. So near this left charge, when your hypothetical test charge is really close, it's going to mostly be influenced by the left charge here. But as you move further towards the center of the triangle, the charge will receive more of an influence from the other two spheres and be repelled out of the triangle. So this line will go in and then curve out and extend towards infinity. And it's going to be symmetrical all around. Part 2. Find one point besides infinity where the electric field equals 0. Often infinity is going to be the reference point for either the electric field equals 0 or the voltage equals 0, the force equals 0. And it just means that it's really, really far away. The effects of these point charges is basically 0 at that point. So another point where the electric field would be 0 is where the force from each of these three charges would cancel out. And that would be at the center of this triangle. Why? Because a hypothetical test charge would receive an equal force from each of the three charges, and they would all cancel each other out because they're an equal distance away and they're all an equal magnitude of charge. Now part 3. What is the magnitude and direction of the electric field at point P? Point P is right here at the top. So we're going to ignore the effects from the charge already located there because since it's already there, it's not going to have any effect to the electric field at that point. So we're going to draw the electric field due to the left and right charges on the bottom of the triangle. Say we call this charge 1 on the left and the other charge 2 on the right. Charge 2 is going to contribute an electric field parallel with its adjacent side to the triangle, and charge 1 is going to do something similar. And I'm going to erase these field lines so we can see better, but they're still there. And we can break these up into components, and we notice the horizontal components will cancel out. Why? Because E1 and E2 are actually equal, because Q1 and Q2 are an equal magnitude and distance away from point P. So these two cancel out, and we're left with just the vertical components of E1 and E2. So I can draw that. And I'm going to drop the numbered subscripts since they're equal in magnitude. We have EY, and the net electric field is going to be equal to the sum of these two horizontal components. So the net electric field is equal to 2 times EY. The physics here is essentially done, and we're just going to finish solving our equations. So net electric field equals 2 EY, and now we have to find EY. So E equals, using our equation above, KQ over A squared. That would be the magnitude of E. Therefore, EY equals the sine of the angle multiplied by E. And from geometry, we know that the angle on an equilateral triangle is 60 degrees. And the sine of 60 is root 3 over 2. Side note here, the vector with absolute value signs over it just means that's the magnitude of the vector. And you can just write it as the normal letter with no vector notation. So, back to the problem. The net force is equal to 2 times EY, which is equal to 2 times the sine of 60 times the magnitude of E. And E is equal to KQ over A squared. So this equals 2 times root 3 over 2 times KQ over A squared. And the two 2's can cancel or reduce to 1. So as our final answer, the net electric field is equal to root 3 KQ over A squared, or roughly 1.7 KQ over A squared. And that would be our final answer. Oh, hold on. Spoke too soon. The direction of E would be straight up. And now, this is our final answer. Now to discuss the motion of a charged particle in a uniform electric field. Well, it's going to be very similar to the motion of a mass in a uniform gravitational field. So we set the electric force equal to ma, because that's the net force, and then the acceleration is the ratio of q to m multiplied by the strength of the electric field. And the electric force may seem abstract to you, but remember, it's just another force, and we can apply Newton's laws to it just like we did in mechanics to the normal forces that you experience every day. Since the acceleration is constant, that means the kinematics equations are valid here. Since the acceleration is constant, the kinematics equations from mechanics are valid here. That's all for now. Thank you.